this section of the course. Here we will be differentiating parametric functions. Now, parametric functions, what are they? They are functions where there is a third variable, a third parameter, such as t, where x is defined in terms of t and y is defined in terms of t. Or it could not. It could be another variable such as theta. For example, in the second example down here, I'm not solving these examples for you yet, but I'm just showing you that x can vary with respect to theta and y can also change with respect to theta, angle theta. So overall dy by dx, because in most cases that's what you will be asked to find. And that's just before there, would to have x written in terms of t and y written in terms of t. Imagine you were an astronomer maybe a couple of 100 years ago, and you were tracking a star that was moving in a spiral shape. So you would be tracking its x position, the and you would be tracking its y position. It would probably be quite confusing to find a function for this spiral shape. But if you just track this x value is moving left and right, left and right, left and right, and its y value is generally moving upsides, right? So probably you would I'm not going to have a guess at what the function is, but you could have simplified it in terms of a third variable. So that's why parametric equations are used. So let's see how do we exactly find dy by changing y with respect to changing x. So dy by dx, or rate of change. If we find the rate of change of y with respect to t, and we can find the rate of change of x with respect to t, we would have another simple such as 2t, and here the change with respect to change of x with respect to t would have been 3t squared plus 1, and we can, as we've done it before with chain rule, if we divide dy by dt by dx by dt, the dt's will cancel away. You're dividing, basically you can action upside down in reverse order, inverted, and the dt's will cancel away. So what you could get there is dy by dx, right? So that's the general formula we're using throughout this section. So let's look at this first example in more detail, because the question will be asking us to actually calculate the gradient of the point P where t is equals to 2. So I already figured out what the rate of change of x is and rate of change of y is with respect to t. We said we're going to divide dy by dt by dx by dt. So if we substitute the values that we find there, we'll have this 2t over 3t squared plus 1, and that doesn't simplify any further. So all we have to do is substitute the value t, which is given to us as 2, into this expression and evaluate this expression at t equals to 2, and we will have found the gradient at that point, which is 13 in our case. Alright, so let's look at another example. In this example here, we are asked to calculate the equation normal to the point P where theta is pi over 3. So I've made this board in bold here because we are not looking for equation of tangent. If this is the curve here, and what normal is 90 degrees to the tangent. Okay, so what we can do with differentiation is figure out what is the gradient of tangent. And if I can jog back your memory to equation of the gradient of normal, normal is the negative reciprocal of the gradient of the tangent line. Alright, so we still need to calculate as normal the gradient of the tangent. So if we differentiate x with respect to theta, what we'll have is 3 times cos of theta, and when we differentiate y with respect to theta, we will have negative 5 sine theta, right? And what we're going to do is divide dy by dx, dy by dx. We have to divide dy by d theta by dx by d theta, so that the thetas uh, are uh, algebraically cancel away, but not literally. We'll still have the function written in terms of theta, the derivative function. So that is negative sine theta over 3 cos theta, and we know that what is cos, sine over cos is tan theta. We have to evaluate this to add theta to x. Now this is going to give us what m1 is. Then to figure out the gradient of normal, we have to take the negative reciprocal of that, which would be minus 1 over negative 5 over 3. So I can see already the negatives will cancel away, and tan theta here, we can substitute uh, pi over 6 there, and if I use my calculator, pi over 6 is, tan of pi over 6 is root 3 over 3, so we have 1 over 5 over 3 root 3 over 3 here. And so these two threes, we can write them on top of the fraction as 9, and we'll have 9 over 5 root 3. Now you could rationalize this and have it written this format here. So it would be these two threes will give us a 3 here. So 9 will cancel away with a 3. So the rationalized form of that is, okay, so the gradient of normal is this. But we were asked to calculate the actual equation of the normal. So we need to use y, actually calculate what x and y are, and use it in this expression where we found m2. To calculate the value of x, or all we have to do is say what is 3 times sine of pi over 6. Sine of pi over 6 is half, so that would be 3 over 2. And y naught would have been 5 times cos of pi over 6. Now cos of pi over 6 is 2, so that's 5 root 3 over 2. Now substituting these two coordinates for x and x naught and y naught, we'll have y minus 5 root 3 over 2 equals to 3 root 3 over 5 times by x minus, our x naught is 3 over 2. And to tidy up this expression, we can add 5 bracket. We'll have 3 root 3 times 5x minus when we multiply these two terms together, you'll get 9 root 3 over 10. And what we have is negative 5 root 3 over 2 on the left hand side. You're going to add it here. 5 root 3 over 2. Now we can get a common denominator here by multiplying uh, this fraction here by 5. So I'm just going to rewrite that as y equals to root 3 over 5x, and 25 minus 9 is 16. So we have positive 16 root 3 over 10. And 16 and 10 can simplify further to this expression. So this is my final answer for the equation of the normal. So I'll see you in the next example.